What is your favorite canteen? Like this? Clean and tidy, spacious and bright. You can order so many delicious foods from the friendly, helpful, and efficiency staffs. However, the reality is crowded and messy, tricky to find a suitable place. It's so awful and terrible experience. Problems like long queuing time, unbalanced preparation of food amount, low service efficiency, and tableware hygienic issues are always exposed in the operation stage of school canteens. Our group's object is to set up an automatic scheme to improve the overall service mode of school canteens, thus enhance service efficiency with the convenient and green lives concept of modern society. In the fun phase, we use process mapping, sorting out the whole process of canteen and prioritize ordinary procedures on which to focus. The students take the tableware, waiting in line, then order in your turns, and staff prepare the meals. After checking out and seated, they start to enjoy meals. At last, they should return the tableware and staff will clean the canteens.
In the simulation software, according to the reality, we abstracted the model and kept the main parts. Students first go into the canteen and go to the counter to order their meals. After that, they can have lunch on the table. Finally, they take the tableware to recycle area and leave the canteen. We assume that students will wait in the shortest line, and the number of students enter there each minute and the time they are eating obey normal distribution. On the dashboard, we can monitor the status and how busy the canteen is. It's easy to find lots of people spend much time waiting, and the students are dissatisfied with the experience here. After a certain simulation time, the result is this canteen can serve 168 persons each hour.
In the measure phase, we use quality function deployment. Firstly, we develop a list of customer requirements like queuing time, dining hall scale, sanitation standards, etc. Secondly, we list and match the functional requirements like staff training, automatic cleaning, automatic dining equipment, etc. Thirdly, we identify the correlations between functional requirements and the roof of the house. Then, we prioritize the customer requirements and functional requirements. Step by step, after the final evaluation, we found that automatic dining equipments, capital investments, self-training, and automatic cleaning should be addressed first.
In order to specify the research direction, our group distributed a questionnaire to a high school in a small town to investigate whether the students are satisfied with the canteen service, and received some feedbacks. About 200 valid questionnaires were obtained. Among them, 184 students were dissatisfied with the existing canteen service. For example, they think the low efficiency of swiping cards will lead to long queuing time, and the canteen is relatively small in scale, so sometimes they can't find a dining place. Also, they doubt the freshness of the food. We arranged and calculated the obtained data, based on which a Pareto diagram is drawn. It can be seen that long queuing time and small canteen scale are the main factors causing students dissatisfaction. Therefore, shortening the waiting time and improving the scale are regarded as improvement opportunities. Also, using fishbone diagram, the root causes of poor dining experience could be found out from the aspects of machines, employees, environment, and so on. Through causality analysis, it is found that the poor dining experience mainly results from outdated machines and crowded environment. Therefore, it is necessary to improve the equipment and space problems in the canteen.
To find the vital S, We decided to choose 3 factors: the number of tables, windows, and waiters in our design of the experiment. We have conducted 16 trials, and we can see the p-value of all these 3 factors are less than 0.05, which means they are all statistically significant in our design of the experiment. Besides, from the regression equation, the number of tables and windows are more significant than the number of waiters. We can get the same results from the Pareto chart.
After the process of Six Sigma, according to the result, we put the improvement into simulation. We increased the number of table and counter, but the data from DOE shows that increase the number of waiter explains little improvement of canteen efficiency, so we don't change it because of cost effectiveness. Instead, we plan to replace the manual recycle area with automatic machine. It can not only reduce queuing, but also save costs. We can see now the canteen can serve about 200 people per hour, so the efficiency has been improved about 20%.
In the control phase, we conduct 30 groups of experiments and collect the data about the number of people served per hour. Then we use IMR chart. It provides process variation over time and helps to identify whether and when the process goes out of control. In our MR chart, none of the individual observations fall outside the control limits. The points also display a random pattern, so the process variation is in control. I-chart assigns whether the process center is in control, and we can see that all points are within the control limits. So, in total, we can see that our process is statistically in control.